Hey everyone, this is Matt with Learn Everything About Design, and in today's video, we are going to be doing a 3D printed rack gear setup. So we did a couple of other 3D printed videos where we talked about standard spur gears, and then we talked about some other different types of gears like the herringbone. We talked about how we could model them in Fusion and design them for 3D printing. I had several comments and requests about doing a rack and pinion setup. So in this video, we're going to go through the process of creating one of those. I will, of course, provide the data set that we create in the video in the description. And as I mentioned in a previous video, we've started a Patreon. So what we're going to be doing is providing some additional data sets on the Patreon. So if you're looking for ways to support the channel, you can check out the link and then we'll include those data sets over there. So the basic idea here is we're going to use the Spur gear creation script that's preloaded into Fusion, same one that we used for our other gear videos. And then what we're going to be doing is talking about how we can use that information to generate and create our own rack and pinion gear setup. Now, rack and pinions are used in all sorts of different places, but the two main areas that we see them are in steering systems, typically in cars, and then we also see them for movement of things like tables for equipment. Now, if you're using this in 3D printing, you're likely not creating a steering system for a 3D printed vehicle because typically you would use something like a servo. That's just a much simpler setup and you don't have to worry about all the interactions and friction and things that happen between the gears. But if you are trying to make this for some reason, then hopefully this video can help. So to get started, we first need to understand a couple of key concepts. What we're doing in this video is going to be designing these for 3D printing. If you're looking to design a rack and pinion or different gears for a machined application, this is not going to have that information for you. The general process is the same. However, the tolerances and backlash and things that we need for 3D printing are very different. And we're not going to be diving into a machined or a manufactured type of ring and pinion setup. So if you want to get started for 3D printing, the first thing I suggest is we create a new component. And this I'm just going to simply call the base component. Now, the reason for this is because the base component is going to be the thing that holds both of these gears in place. It automatically gets activated. This is just what happens by default in Fusion. When you create a new component, you can turn that option off here. But generally what happens is I create it before I remember to deselect it. So I always have to go back and reactivate the top level of our design. Also note, by default in Fusion, the anchor icon here means that it's ground to parent. In this case, that's fine. That is a setting you can toggle off in your preferences, or you can also right click and unground from parent. There are some benefits to using ground to parent. I typically unground things pretty much right away. For this example, it's going to be fine though. The second thing we need is a gear. Now, the gear that we're going to be using comes from the utilities menu, from our add-ins, and we're going to go to a script. Now, what has happened in Fusion is the scripts and add-ins dialog has changed quite a bit. You can filter by scripts if you want to. You can do ones that are installed, ones that are running from startup, ones that are created by me. The one that we're looking for is actually in the samples. So you can toggle to scripts and samples, and then you can find Spur gear. Now, there are two here because one of them is in C++ and one of them is in Python. You'll get the same exact result out of either of those. I typically run the Python one, but again, it's going to be the same either way. When we get into designing a Spur gear, there are a couple of important dimensions that we need to understand. First is going to be the pressure angle. There are some defaults here and a custom. We're going to be leaving this at 20 degrees. And the reason that we need to understand this number is because the 20 degrees is also going to be the angle of the tooth that we create on our Spur. It's not going to have the arced sections like we do on the Spur gear. It's going to be straight, but we're going to be using that angle. So if you happen to set it to 14.5 or 25 or some other number, make sure you know what that number is because you're going to be using it. The module number is also important. This is going to drive the overall size of each tooth and ultimately the overall diameter of your design. So you can see here that for 24 teeth, a module of 12.7, we get 304 millimeter pitch diameter. That means that this thing is not going to fit on pretty much any 3D printer. So we need to make it a good bit smaller. And what we're going to do is generally I would set this to either a module of 1 or 2. A module of 1 is going to give you a relatively fine tooth. This is kind of the same value or number we used when we did our original gears for 3D printing. So if you're trying to interact with gears you've already created, then try to go back and remember those numbers. In this case, a module of 1 is going to be what we use. If you do a module of 2, you'll get a quite a bit larger tooth. And I'll put a little picture on the screen here showing what a module 2 and a module 1 kind of look like. So for the same or roughly the same diameter, what you'll need to do is double the number of teeth if you are using a smaller module number. So for example, if we have a 20 millimeter or 20 teeth with a module of 1, the pitch diameter is 20 millimeters. If we set the module to 2, we need to go down to 10 teeth to get to that same pitch diameter. And the pitch diameter is the place where the gears interact. So it's essentially, think about it as the contact point. So as you're designing these, make sure that you play around with these numbers, make sure you understand what they're doing. You might have to create a couple of gears before you can visualize it. I wish there was like a preview image on the screen. That would be great if it like live configured the sketches, but we don't have that. There is a backlash number here, and that can be used to sort of influence the tolerance that you need for 3D printing. So what I've found to be the most helpful is to leave that at 0 and then have that backlash or that tolerance value incorporated into the gear or the tooth that you create for the rack. So I generally leave it at 0. If you want to introduce a little bit of slop between gears, you can do it with that number. But keep in mind that when these get created, there is not a fully defined sketch. You get a sketch, but all the geometry is created in the script, which means that if you have a 12.7 millimeter diameter circle, you just get a circle. It's not even constrained to the origin in our sketch. So it can get pretty messy if you try to rely on that. I personally tend to do it inside of my new designs or my new sketches. That way I can configure it and change it if it doesn't fit. The root fillet value, I tend to keep this pretty small for what we're doing here for 3D printed parts. Not for any real reason other than when we have a module of 1, the tooth size is pretty small. So I don't want to use a fairly large fillet because then some of the tooth is going to start to disappear. Now this root fillet value only affects this bottom corner. So if you make it too large, you can actually end up with a complete round section in here. And there will be a point when just it doesn't physically work in the sketch. For the gear thickness, I'm going to use a value of 10 millimeters for our sample, and that just kind of keeps it big enough so that we can play around with it and have enough material to play with. It doesn't need to be that thick, but keep in mind with 3D printed parts that the load and the wear that happens on the side of them, that is going to have an impact on how well these things work. So if you make them really narrow, if you make it 5 millimeters or less, and you have a small tooth like module 1, then you're likely going to have to worry a little bit about the longevity of those things. As you start to make the module bigger, so if you make the module 2 and you have that larger tooth there, then they tend to be a little bit more dependent on things like the number of traces that you have in the 3D print slice setting. And that way you can really configure and play around with the strength of the gear on the print setting side. But on the smaller side, we really kind of have to worry a little bit more about the geometry, like the fillet radii and things like that. So now that we have all of these settings configured, a 20-degree pressure angle, module 1, 20 teeth, half a millimeter root fillet radius, gear thickness of 10 millimeters, and a hole diameter in the center of 6. And really, I'm just using that as a starting point. We can make it bigger or smaller later if we need to. I'm going to say OK, and this is going to create a component for us. I'm going to go back to my solid tools, and notice that this is set up with the orientation of it facing the top. You can rotate the gear if you want to about the origin. Really, it doesn't matter too much for what we're doing, but you will notice that it can sometimes be a bit of a pain to rotate with it in the top orientation. So sometimes you might want to go and set the current view as front, and then you'll find that your your free orbit rotation is a little bit easier, and you don't tend to get lost around that vertical z-axis as much. It just behaves slightly different when it's front versus top. So just keep that in mind. Before we go too much further, there's another thing that we have to do. So we're going to activate the spur gear. I'm going to go in and expand the sketches. Note that we've got the sketch 3, which is the pitch diameter. So if you're putting multiple gears together, that's where you want the pitch diameters to be tangent to each other. If it's too far away, then you're going to have a lot of backlash or slop in it. If it's too close, then it's probably going to bind. So what we want to do here is we want to create a new sketch. I'm going to create this sketch on that front plane. In this case, it's XY. And what we're looking to do is rotate the gear so that this, let me zoom in here, this vertical line is actually vertical and lined up with the Y-axis. So the way that we do that is we're going to create a sketch, and we're going to draw, let's just say, a vertical line. And then I'm going to hit escape and actually project this. So P on the keyboard, or come down to here and project it. And then we're going to draw another line. So L on the keyboard and up to here. Now, the main reason that we want to do this is we want to know what the angle is between these two lines. So D on the keyboard for the dimension, it's going to create a driven dimension, 5.4 degrees. So why is that important? Well, when we start to create the rack gear, we need to know, we need this to be vertical to help us with the creation of that geometry. If it is rotated, then it's going to be much harder for us to do this on the fly, designing these for 3D printing. If you know all the formulas and you understand how the two gears interact, you could do it without rotating it. But I personally find that it's easier visually to rotate it. So we want to go 5.4 degrees. You can right click on the sketch and show dimensions if it helps. But what I'm going to do is select the body inside of this component, and I'm going to go to Move Copy. I'm going to set the pivot point at the origin of the gear. And let's go ahead and right there, click the green check mark. And then we're going to click the Rotate button and 5.4 degrees. It went the wrong way, so I'm going to hit minus. And what we should see is that vertical line we drew should now be hitting or relatively close. These numbers aren't going to be perfect, but it should be relatively close to hitting that vertical line or that straight line section of the gear. So we're happy with that. We're going to say okay. And you might be thinking to yourself, why did you rotate the body instead of rotating the entire component? Well, the main reason for that is because I did not want the origin of the component to rotate. So if we happen to rotate the entire component, that 5.4 degrees, when we go to create a new sketch, the coordinate system of the spur gear is going to be rotated along with it. If we rotate the body inside of the component, then the body itself rotates as a feature in the timeline, and we don't have to worry about the coordinate system getting shifted. The whole purpose of this, or the whole intent of this, was to make sure that the coordinate system or that edge of the gear lines up with the coordinate system. So I don't need to see that sketch anymore, but now we know that this tooth here is completely vertical, and we've gone back and activated the top level of our design. The next thing that we want to do is create a new component for the spur gear. So again, assemble new component. We're going to call this one, rack, not spur gear. We're going to call this one the rack, and we can go ahead and activate it. So there are a couple of things that need to happen in order for us to make this rack work. And I don't want to dive too deep into all of the different definitions and nuances, but there are a couple of really important things that we want to do. But first, let's get started with a sketch on that front plane. We are going to bring over the pitch diameter. So again, you can use P on the keyboard or go to Project Include. Then I want to go back to the spur gear and hide that sketch. And the main reason for that is because it makes it difficult for us to select this and convert it to construction if we've got multiples on the screen. You can always hold down the left mouse button and bring up a little dialogue of all the things under the cursor, but it's just easier this way. So what we have here is the pitch diameter. Now remember, the pitch diameter, if we had two spur gears, that's going to be where they contact each other, where the teeth contact each other. When we're changing from a circular profile gear like this to a linear gear, this is going to be the pitch line. So this line right here. And I'm going to convert it to construction. And I'm going to select both of these and make them tangent. So this is essentially where the center or the contact point of our tooth. I don't want to say center, but the contact point of our tooth. I'm also going to toss in a vertical construction line. We're going to convert it to construction. Again, X on the keyboard will do that for you. And then I want to use the midpoint constraint for basically making sure that those are at the midpoint. You can see there is a little triangle there. For whatever reason, these constraint icons always tend to go over each other. You can hold down the left mouse button and you can also get the constraint icons, because this is oftentimes a big problem when you start stacking geometry like this. But the reason for this is because as we define the length of our rack in the rack and pinion setup, then we want it to be centered here, because that's going to help us basically locate everything in that middle tooth that we're creating. The middle tooth will be slightly offset from the middle or the center of that line, but that's okay. All right, so we've got a couple of references. There are a few more references that I want to create that are going to be helpful for us. So I'm going to draw another circle, and we're going to go ahead and just put it right there. This is typically called the base circle. Let's go ahead and hit escape, and we want to convert that to construction. We'll talk about what this does here in just a little bit, but that base circle reference is going to help us understand basically there's a line of contact where the points go from one gear to the other, and it's going to be defined partially by the tangency of this line. So we just want to have a circle that's kind of floating for right now. A couple of other references that we want to add at this point. We're going to go to our sketch points, and I want to add a sketch point on our pitch circle here, and I'm going to add one down here as well. You notice that these two lines are relatively close here, but I'm going to add one. It's going to be really hard, but I'm going to maybe stick it over here and hit escape. We also want to project this, so P on the keyboard to project it, and then we'll convert it to construction. And then we want to use our coincident constraint for this point on that curve and this point on this curve as well. So what we have here is the contact point on the pitch diameter that is going to represent the pitch of the teeth. Now, the pitch of the teeth is something that's important because as we go ahead and translate the circular gear to a linear one, we need to know what that distance is in order to use it for our pattern. So I'm going to use the dimension tool, and I'm going to go from this point to this point, right click and make sure that it's aligned, and then we're going to make it a driven dimension. So in this case, it's 3.129 millimeters. Now, it's 3 decimal places. That's going to be the default for the dimensions here in Fusion. That means it's likely got a lot more decimals after that, but 3.129 is going to be close enough for us. If you happen to be making a 3D printed rack that is hundreds of millimeters long, there may be an accumulated error or a difference in those as you get further and further away. But for our purposes and the sizes that we would be concerned with for 3D printing, the 3 decimal places is more than enough tolerance for us. All right, so now we've got the distance between those. That's going to be our contact points. A couple of other things that we want to add are some references for the height of our new gear, and then we want to start to define it. So let's go ahead and add some lines. So I'm going to add a horizontal line here. I'm going to add a vertical line from the midpoint. And then I'm going to add a line that comes down at an angle here and down at an angle here. We'll go back and we'll fully define these all in just a minute. I also want to come in and add another point on that pitch diameter, hit escape, and then project this. So again, P on the keyboard, X to convert it to construction, and then I want to shift select both of those and snap it to there. The main reason for this is we are going to be using that point and the distance to the right side of this tooth as our 3D printing tolerance. So typically 0.2 to 0.4 millimeters. That's going to be enough of a gap to where our 3D print doesn't bind up. 0.2 is a bit on the tighter side, and you will notice some nuanced differences depending on the orientation that you print these parts in. And 0.4 generally is going to be kind of sloppy, but it will generally work a bit easier with less friction. This vertical line here, let's go ahead and hit escape. Let's select it, turn it to construction. Now we can start to define these angles. Now, remember when we created that first gear, I said to remember that pressure angle, that 20 degrees. That's going to be used to define the angle here. So we're going to go from this line to this one, and that's going to be 20 degrees. This one over here is going to be the same. We could use the symmetry constraint if we wanted to. So for example, you could select this line, and the center and apply a symmetry constraint. You could also do a dimension over there and then click on this one or make them equal. Either is going to be fine, but really the main thing that we want here is we want to be able to ensure that both sides are the same. The other thing that we want to do now is we want to add a dimension from that point to this line. And this is going to be our 3D printing tolerance. And this is generally how I do it for something like this. I want to add this backlash or this gap between the parts. And again, 0.2, pretty tight. And you'll notice that as you use these gears and you use them more and more, they'll start to loosen up and work a bit better. 0.4 will work better instantly for this sort of module 1 gear. If you're using a module 2 or bigger, so you've got fairly large teeth, then this 0.2 should be plenty and things will move really smoothly. So it really comes down to figuring out your printer and also understanding the sizes of the geometry that you're working with. So escape to get off our dimension tool. And now that we understand that, we can begin to pull this around. And what we're really looking at is this line should be somewhat tangent to this arc because this is the position where we've got the pinion or the spur gear. Let's say it's rotating counterclockwise. That is the point at which it's contacting this gear that's on our rack. That's where the most amount of force is coming in because this is going to have the highest point of contact as it's rotating around. So we can either make it tangent to that arc, or because we added that point and it's going to be close enough for what we're doing, we could make it coincident to that point. So that's going to fully define that left side. The top can still be, hit escape, the top can still be moved up and down, which is going to dictate how wide this is. The difference here, this is really going to be a bit of a gap. We don't want these to be exact. We want to have a little bit of gap between the gears because as they're rotating around, you don't want this to bind with that. That's going to instantly spike the load here. It's going to make it be very hard to move. So you do want a bit of a gap here. The amount of gap depends a bit on the geometry you're working with. For us, I'm going to go ahead and dimension basically from the origin there. And I'm going to set it at 9.5 millimeters. And at 9.5 millimeters, there's a pretty big gap there. You can make it smaller, you can make it larger, but the main thing that we want to make sure we understand is this is the point of contact with the spur gear or the pinion. And we need to make sure that we've got material above that point. These corners will get rounded off. So play around with the numbers. If you're doing a different design, let's say if you're using these exact dimensions in your print, then probably I would lean to 9.25. But again, 9.5, 9, you just have to play around with them. So that's pretty much it, honestly. We know this is going to be the value here that we're going to use for our basically our linear pattern. That's going to be 3.129 between the teeth, or the spacing between the teeth. Some other helpful bits of information are going to be, let's go ahead and draw another line here. So let's start up at this base circle here and come down to the right and then say, okay, hit escape and make this construction. So this line is going to be essentially the line of contact. So as we're going from this circular gear to a linear one, we're going to have multiple points of contact, or essentially a handoff that happens. And the handoff is going to happen along this line. And what needs to happen is this line and the circle need to be tangent. And the angle between this line and the horizontal is going to match our pressure angle, that 20 degrees. And so what this tells us, if we look at this, this is going to tell us exactly where those points of contact are. So this line and this point here are going to be intersecting. And what we're going to see when we start to animate this, because that line is going to rotate with the gear, what we're going to see is we're going to see where those points of contact end up happening. So some other things that need to happen, of course, we need to finish off the geometry. So I'm going to go ahead and draw, and let's go ahead and let's do a rectangle. So I'm going to draw a rectangle. The rectangle is going to be 3 millimeters tall. So again, a decent amount that we can print. Then we need to really think about the distance that this is going to be from the end of our spur gear, our rack gear. And the way that I typically would do this is I'll draw another circle, and then this is going to be construction as well. And we'll make this tangent to our horizontal line. The size of this is going to be dependent on the diameter of your gear and some other factors. And so those other factors, I'm going to go ahead and select this bottom edge here and hit P on the keyboard to project it. And let's do an aligned dimension. So right click, aligned. It's going to be driven. So basically it puts it in brackets. This is a reference because it's not changing any geometry. But basically we've got about 0.7 millimeters width. And the outside diameter of, let's go ahead and we'll just draw another circle. The outside diameter of this, again, make it construction, dimension, driven, 22 millimeters. So the way that I typically would go about this with a module 1 gear is to take this number, 0.7, and double it. So we got roughly 1.5, 1.4, and then add that to the diameter here. So what we're going to do is we're going to say 22, even though it's a reference, we can use it, plus, and I'll put in brackets, this number times 2, and close the brackets. So what this is going to give me is roughly 23.5 millimeters. If you want to just manually enter a number, that's fine. But this is probably going to be the smallest distance that I would make this edge from this gear. And the reason for that is because right now, it looks like it's pretty far away. But once we start to pattern this gear and we add fillets to those bottom edges, the distance between the end of that spur or pinion gear and the bottom or the root of those two teeth is going to be pretty close. So as you play around with these, you need to play around with these numbers and the values that you have for things like your fillets. I'm going to go ahead and just make sure that these are connected here. But, and again, the reason for this is because as we round those corners off, they're going to start to bottom out. And as that gap gets smaller and smaller, you'll find that it's harder and harder. The friction will ramp up, the loads will ramp up, and it'll be harder for this to work. So again, that's kind of the minimum I use. Double that number and add it to the diameter. Now that works for a module of 1. Now if you make the teeth taller, a module of, let's say, 2, then typically what I'll do is I'll double that number, but I might end up adding it to the radius instead of the diameter. You kind of have to play around with the sizes that you're working with. So if you're making something quite a bit bigger, you will likely just have to add more of a gap there. I don't have a good number because everything is based on the width of these teeth, the radius value that you use in the root. But the main thing here is that you don't want to make it too tall because then it'll just make the teeth weaker. And you don't want to make it too small because then it'll bottom out and it'll start to load up. All right, so now that we've got all that, let's go ahead and finish the sketch. I didn't give this a full width and it's not actually centered, but for our example, it's going to be fine. So what we're going to do is we are going to extrude this. You can do this one of two ways. You can extrude the base first and then come back and extrude this and join it together. The reason that I would do that is if I want to pattern the feature, then I would go about doing it in 2 separate steps. What I'm going to do instead is hold down Control, select that, and do it all at once. I am going to hide the spur gear. I'm going to use a fillet, so it's F on the keyboard. We'll select these bottom and these tops, and I'll try 0.5 millimeter. So it gets me a pretty good round fillet there. And then we're going to go to do a linear pattern, and we're going to change the object type to faces. So include all the fillets and all the flat sections. And then for our axis, it's going to be this bottom edge. We're going to set this to spacing, which is going to be the distance between. And then that's going to be the value that we used for, let's go back to the sketch. We're not going to be able to turn that on. Let's hit cancel for a second. Go back to your sketch, right click and show dimensions so we can see. It's going to be, where is it? This value right here, 3.129. So if you don't write that down, you might want to make sure that you turn the sketch on before you get to this stage. So select the faces again. We'll just grab all of these, rotate, and then bottom is our axis. And now our spacing is going to be that 3.129. And we're going to do this symmetric. And then we can just use this to start adding more teeth to it. We'll say OK. Can hide the sketch, bring back the spur gear, and we'll go back to the top level. All right, so at this point, let's go ahead to assemble as-built joint. We'll set this to revolute, the gear to the base. There's no geometry in the base, but it doesn't matter because all Fusion really cares about is the coordinate system. We're going to say OK, right-click and repeat that. Now we're going to do the rack and the base. We'll set it to a slider, pick that bottom edge in the center. We'll say OK. And then we're going to create a motion link. So between the revolute and the slider, we're going to go to our 360 degrees and we're going to divide it by 20. That's the number of teeth. You probably have to reverse this. And then the distance is going to be the value that you used for your pitch. So for every tooth, so 360 degrees, the full revolution of the gear, divided by 20 will give us the degree between each tooth. That's going to move the linear axis 3.142 millimeters. And again, that comes from this one here. So as it's different, let's go, this should be 3.129. We'll say OK. So as we move this, what we should see is the gears mesh like they should. Now it's not going to be perfect. There might be some slight overlap based on the geometry. You can see there's a tiny bit of overlap there. But we've got this gap here, that 0.2 millimeters, and that's our print, basically our print tolerance. So it gives us a little bit of leeway in properly defining these gears. So what I was talking about with this line of contact here. So as we go, and we'll see it right here, as we go, that's the point in which the two gears contact. And as we continue to go, it'll be the same on the next one. And if we happened to not have that 0.2 millimeters, if we tighten that gap up, you would see that where this line contacts multiple gears is actually where those points of contacts will be. So I'm going to revert the position and we'll go ahead and hide that sketch because we don't need it anymore. So that's the basic premise of creating a rack and pinion gear, one using the Spur gear script creation tool that's built into Fusion, and then kind of backing out of the numbers that it gives us or the geometry and building the rack. So what I'll include in the description of the video and the downloads, I'll toss this little sample here, which you'll see on the screen as a little 3D print. So this was done using a module of 2 with 10 teeth. So you can see the gaps are a bit bigger. You can kind of see that we still have that 0.2 millimeters in there, but this works pretty well. And having those taller gear, the teeth on the gears will give us a little bit more of a buffer for how well and how smooth this works. So this is a nice little one that you can just 3D print and try out and see how it works. I will also include a sample, this one here. I'll also toss this file in. And if you want to build out the base to connect everything together, then obviously you can go ahead and do that. And again, this one was done with 20 teeth and a module of 1. And the other one was done with 10 teeth and a module of 2. So roughly the same diameter or pitch diameter, pretty close anyways for our purposes. And we've just got basically a 1-to-1 ratio for For this, 10 teeth and the size of the teeth down here. And again, as I mentioned on Patreon, what we're going to start doing is providing data sets on Patreon that you can buy for a few dollars to support the channel. These will typically have some more data sets that are built out a little bit more completely. So for example, this one has two mounting points here for the centerpiece, and there are little mounting holes on the end of the rack. There's also a little knob here. It's got a square drive on it, and you can put that in and drive the pinion gear to rotate this. And if you go to the modify change parameters, what I did on this data set was this is driving, we've got a print tolerance value here. So if you find that you need a little bit more of a gap, what you can do is you can drive the gap between the parts if you find that 0.2 is a little too tight. And what that does is it actually changes basically the overall gap between these. You can see here it gives you a little bit more spacing. And the other thing that this file has is the number of teeth and the overall length of the rack itself can be driven by changing the number of teeth here. So what that'll do is it'll shorten everything. The holes and the tabs on the end will shorten, and you can increase it or decrease it. I haven't tested where the limit of that is yet, but you can play around with it. The one that I printed had 20 teeth, and that works pretty well. So it's a good little test that you can use and play around with and see how this works. This one was done using the same parameters we just used to create this. So it used 20 teeth, module 1, and should be roughly the same geometry. This the rack piece gets slid in from the side, so it's captivated or it's captured, and then the gear gets installed. And if we hide the holder, you can see that there is a square drive in the center, and I also removed some material. One of the reasons that I tend to do this with gears and things like that, when you're 3D printing, this will actually create a couple of extra passes or traces around those openings or holes. And a lot of times that's going to be stronger, especially near the teeth, than if it just had a bunch of infill in the center. So if you are looking to support the channel and you like this content, you enjoy it, and you're looking for another data set, this will be on Patreon, and I'll leave a link in the description. And like I said, generally it's a couple dollars. $3 is the lowest value that will let us put on Patreon, so everything will be at least $3. If you have any questions, please leave a comment below. And if you want to see anything else, we'll always add the comments to our list. We have a long list of videos to get through, but if there's something specific you want to see, whether it's 3D printed gear related or something else, leave those comments as well. As always, thanks for watching, and we'll see you in the next one.